Greetings, everyone. This is Professor Norm Jones, Brigham Young University, and in this video we are going to review the mountain lake model exercise associated with CEEN 547 groundwater modeling at Brigham Young University. And the objective of this exercise is to build our first simple groundwater model using the GMS software. And this will be a MODFLOW model. And this is the description of the problem. So what we have here is a mountain range on the right, and this mountain range will correspond to a no-flow boundary condition. And then on the left we have a lake, which will be a specified head boundary condition. And then in the middle we have this alluvial fill, and so what's going on is we have recharge coming in, so precipitation coming in to the top of our model, and that provides our source of water. And then since there's a no-flow boundary on the right, that groundwater table mounds or builds up in elevation, and then the water flows from the right to the left over to the lake. So really simple model. And we're going to simulate this with a rectangular model. So the groundwater flow direction is one-dimensional from right to left. So we're going to have a parallel flow boundary on the top and the bottom in the direction of flow. That'll be a no-flow boundary. And we're going to represent that with a grid of 100 cells in X, 75 cells in Y, and then it'll be a one-layer model, so keep things really simple. And we have these other inputs at the bottom. We're going to have a top elevation of our grid of 3,200 feet, bottom elevation of 2,700 feet, hydraulic conductivity of 2 feet per day. And then we've got some other information about recharge, etc., which we will we'll tackle a little bit later. But so let's go ahead and start working on this, and we're going to do this using the GMS software groundwater modeling system. And this is our first exercise using GMS. So we'll take a second and kind of explain the layout. So this is our main window here where we're going to be entering data and displaying the model results. And on the left we have, this is the Project Explorer window. So this will represent a kind of a hierarchical representation of our data, and that will be populated as we start creating data. And then of course we have our menu commands up, our menus up here, and we have this tool palette of shortcuts to frequently use menu commands. And then we also have these modules, or these little icons right here, represent the different modules in GMS. So GMS is split into modules depending on the type of object we're dealing with. So we have one for triangulated irregular networks, boreholes, three-dimensional volumetric models we call solid models, 2D finite element meshes, 2D structured grids, scatter points, 3D finite element models, 3D grids, 3D scatter points, and then a map module for GIS data, a GIS module for importing data from ArcGIS, and then an unstructured grid module for dealing with unstructured MODFLOW grids. So we're going to deal with, we're going to use structured MODFLOW grids. So we're going to start out here in the 3D grid module. And to create a grid, we can do one of two things. Oh, by the way, before I continue, when you click on a module, you'll notice that it changes the menus that are visible, and it also changes the set of palette or tools down here on the dynamic tool palette. So, and we're going to mainly be working in the 3D grid module. Later in the semester, we're going to learn about the 2D scatter point module and the map module, but for now we're going to stick with the 3D grid module. So the first thing we're going to do is create a grid, defining our problem domain. And we can either go to the grid menu and select create grid, or we can right click in the Project Explorer window and select new 3D grid. Either one of those will bring up our create grid dialog, where we enter the properties of our grid. And if we pop back here for a second to our window, it says we want to have, in the X direction, we want to go 20,000 feet, so about 4 miles, 100 cells, and then in the Y direction, 15,000 feet, 75 cells, and then the vertical thickness, 500 feet, 1 cell. So let's enter that in here. So we have 20,000, and oops, excuse me, this is the origin. I should leave that at 0. So that's the origin is like the lower left corner of your grid. And so we're going to leave that at 0. Now later in one of our exercises we'll start talking about real-world coordinate systems and using base maps. So we're not using a base map here, so we're just using a local coordinate system. So we're just going to leave that at 0. Okay, the length. This is what we're talking about. This will be 20,000 feet and 100 cells. And by the way, you'll notice that it puts these little labels next to my inputs that telling me what kind of units are expected, and right now it's feet. You can change that, of course, to metric units, and I'll show you how to do that in a minute. Okay, length in the Y dimension is 15,000 feet, and we want to have 75 cells in that dimension. And then in the Z dimension, we want this to be 500 feet. Now, by the way, the bottom of the grid should be 2,700 feet and the top 3,200. So if we wanted to, we can change this right now to 2,700 feet as the origin. The origin is the bottom of the grid. And so if we do that, then the bottom will be 2,700 and the top will be 3,200. There's a way to edit that later, which I'll show you, but for now, we're going to enter it like this. So now we're going to click OK. And let's see, where's our grid? The grid was created. There it is. I had to center it. For some reason, it created it off screen. And so what I did is up here in the right below the flow part of MODFLOW, there's a little, it has a magnifying glass with 4 corners on it. It says frame image. So let's say, well, whatever you have, zoom to that. Now you can also there's a zoom to command, zoom to extent. You can do it right here, or if you go into the display menu, there's a frame image command as well. So you can do that either way, and I'm not sure why that appeared off screen. So here's our grid. It has again 100 cells in the X direction, 75 in the Y. Got the right dimensions. If I switch to front or side view, you'll see that it's just a 1-layer grid, and these tools here allow us to do that. We can also, we're currently in ortho mode, so we're only looking at the front, top, and side here. But if we switch into out of ortho mode, let's see, we can go into this view, which allows us to, if I use this tool right here, allows us to rotate that around in 3D, which is kind of fun, but for now we just want to go back to ortho mode, meaning we're always going to look into top, front, or side view. Alright, what we normally do here now is we do File, Save As, and I'm going to go to my C drive, and then I have a temp directory, and it looks like I've already saved this here before. I'm going to go ahead and delete that so we don't get confused. And so I'm going to save this as mountain-lake, mtn-lake.gpr. GPR is the suffix for or the file extension for a GMS project file. So I'm going to click save there. And let's see, I got to go up. Let's temp. Select that one more time. And for some reason it thinks it's up a level. There we go. Went ahead and saved that. And okay, now we're ready to continue on. So we've created a grid. Now it turns out that GMS supports different kinds of models, and it also supports things like three-dimensional interpolation of contaminant plumes, which use 3D grids but aren't associated with a model. And so creating a MODFLOW model is kind of a two-step process. You first create the grid, like we've done, and the second step is to go to the MODFLOW menu here and select New Simulation. What this does is it generates a MODFLOW simulation object, all of the arrays and input data associated with a MODFLOW simulation, and it creates that along with your, and it associates that with your 3D grid. And so here we go. We can give it a title. We're just going to leave that as a default. You can pick which version of MODFLOW you're going to use. We'll just use the old MODFLOW 2000 for now. And another things you can do is you can select your packages, and this is going to be a steady state model. So I'm going to click on the packages button, and what this does, it lists all the different packages that we want to use, and this is going to depend on your inputs and what's going on. But for the flow package, we almost always leave that as LPF, layer property flow. We have a number of solvers we can pick from. The default is a PCG solver, which should be fine for this case. Now over on the right, you have all of your optional packages, and some are dimmed because they're dependent on which version of MODFLOW you're using. But let's see, I'm looking down through here. We probably need the recharge package because we have some recharge in our input, and the well package, and I think that's about it for now. Actually, we'll turn that well package on later. The first instance we run of this, we're just going to use recharge, so we'll click OK. And also there is a top and bottom elevation button here, so if we click on this, it brings up this dialog that shows us our top elevation array. So every layer in your MODFLOW model has an array of cells for the top elevation and one for the bottom elevation. And so we have a one-layer model, so we can just look at one array here. But if we had multiple layers, we could use this little controller here to switch between our arrays. And that's already defaulted to 3200 because of the way we created our grid. We created the bottom at 2700 and the thickness at 500, so that puts our top elevation at 3200. And so we're okay, so we'll click cancel. Otherwise, we could say, we could do constant to layer and enter a new value. For example, I'm going to change this to 250 for a second. You'll see how that changes. Or theoretically, you could come in here and change these one at a time. You don't normally do that, but you could. And so I'll change that back to 3200 and click OK. And likewise, the bottom elevation is already defaulted to 2700. Another thing you kind of need to worry about are your starting heads. It's possible to go in and define an array of starting heads. You'll notice these are all dimmed. It says dialog is not editable because starting heads are set to match top elevations. A few years ago in GMS, they added this little option here, starting heads equal grid top elevation. That's turned on by default. And what that does is it initializes your starting heads to equal your grid top elevation, which is a pretty good default in a lot of cases. Now, starting heads are used to initiate the solver, you have to enter a guess for all of your heads in your grid, and then the MODFLOW solver will take that guess and iterate until it converges on a solution. And so we're just going to use the starting heads equal grid top elevation, and that'll pretty much give us everything we need. Some other things that we can enter here are the units, and as I mentioned before, it's defaulted right now to feet per our length unit and days for our time unit. We could change that to years or whatever you want, but we're going to keep it on feet and days. And the mass, force, and concentration units we rarely have to worry about that. Now the units, all that does is it makes sure that the labels that are displayed on the inputs are giving you the proper prompts. That's all it does. So for example, it says units of feet here. If I change my length units, that prompt would change accordingly. Okay, here we go. Now every time we make a change, we can go up to the file menu and click save, or use Control S, or there's a little shortcut button right here that will save our changes for us. Alright, the next thing we are going to do is enter our properties. We've already confirmed that our top and bottom elevations are correct. We need to enter hydraulic conductivity of 2 feet per day, and there are a couple of ways we can do that. Hydraulic conductivity is associated with the layer property flow package, and that is the LPF package. And I can get to that in a couple of different ways. I can go up here and select to the MODFLOW menu and select layer property flow, and then there's a button here that allows me to edit my horizontal hydraulic conductivity. And I'll select now constant to grid. What that does is it prompts you for a number, and it enters that. I'm going to enter 2 for 2 feet per day, and it enters that in the entire grid. There's also a constant to layer, so it's possible that you could have like a 3, 4, or 5 layer grid, and constant to grid assigns it to the value you enter to every cell in the entire array, including all of the different layers. Constant to layer would only assign it to the currently visible layer. Well, in this case we have a 1-layer grid, so it doesn't really matter. We can do it either way. There's also these other buttons, 3D data set to grid. This allows you to take like a MODFLOW solution or some other generic data set and copy it to your to this particular array. And a data set in GMS is just it's like an array. It's kind of like a raster if you have a GIS background. It's just what we call a set of values that are associated with your grid in array format. And yeah, we don't need to use that option this time, but we'll refer back to that later in other exercises. Alright, so we click OK. There's also a horizontal anisotropy factor. This is a ratio of the hydraulic conductivity in the rows versus the hydraulic conductivity in the column, so kind of a KX versus KY thing. And we generally leave this as 1, but it allows you to define some horizontal anisotropy if you'd like to do that, but we'll leave that as 1. Now, by the way, you'll notice over here in my Project Explorer window, I have some shortcuts to some frequently used MODFLOW arrays. If I double click on this one right here, it'll bring up the top elevation array, bottom elevation array. We have starting heads and I-bound, which we'll get back to later. And there's a section for the LPF package, and if I double click on HK, that would take me right to that hydraulic conductivity array, which we edited just a second ago. So, alright, we're all set for that. Save those changes. And our next thing we need to worry about is the recharge. And it says we have 20 inches of rain per year, and we're going to assume that 15% of that reaches the aquifer. And so the first thing we need to do is take this input, or take these numbers and convert it to input in the proper format for a MODFLOW simulation. So So here we go. To do that, I'm going to bring up Microsoft Excel. And so I'm going to say rain. We have 20 inches per year. And infiltration is 15, let's see, 0.15, 15%. So we'll mark that. And so our recharge will then be equal to 15% times 20 inches per year. So 3 inches per year. However, we need to convert that into feet per day. And so we have to get it in the right units. And so we're going to take that number and we're going to divide it by 12 and multiply it by 365. And that gives us, let's see, we need to divide it by 365, excuse me. Here we go, 0.000685 feet per day. I'm going to copy that to the clipboard. And I'm going to go back to GMS, and we can get to our recharge rate in one of two ways. I can go up here and select optional packages, recharge, and that brings up the recharge package editor. Or I can just double click on recharge rate right here and it brings up the same thing. And again, we've got this array that we can edit. But the recharge array, it's not three-dimensional, meaning whether you have one layer or multiple layers, it's just a single array representing the amount of water infiltrating into the top of each vertical column of grid cells. And so we are going to select constant to array, and then I'm going to paste that number. Whoops, it looks like it didn't copy, so it was 0.000685. Come on, 0.000685, and oops, let's see, I got to get a decimal point in there. There we go. There's our recharge rate. So we'll save that change. And what else do we need? We need some boundary conditions. So I mentioned in the introduction that over on the right we have a mountain range, and on the top and bottom we have no flow boundary conditions. And so those are all no flow boundary conditions. The mountain range, we have a bedrock outcropping there. And so the default boundary condition for a numerical model like this is no flows. We don't need to do anything for those three boundaries. But over here on the left, let me bring this diagram back up. On the left we have this lake, and the lake has an elevation of 3,000 feet, so that will be a specified head boundary condition on the left. So we'll come back here, and what I need to do now is select all these cells on the left, and I can do that by using, I have the select cell tool right here, and if I can click on individual cells, or if I hold down the shift key I can multi-select a region. I can also drag a box, so anywhere I drag a box it selects all of the cells in that box. So if I drag a box that just includes that leftmost column, it selects them. There's another way to do this. There's actually a select row tool and a select column tool. There's also a select layer tool, but if I use the select column tool, I just click anywhere in that left column and it will select the entire column. Now once they're selected, I'm going to right click and select properties, so cell properties. And because what I need to edit here is the I-bound array. The I-bound array, as we've learned in our lectures, defines the active and inactive zones for our model. Now all of these cells are going to be active, but a negative I-bound value also indicates that the cell is active but associated with a specified head boundary condition. So I'm going to change my I-bound to specified head, and then that changes the actual value to go to 0 or to -1. I mean, you could enter the the value directly if you want, but GMS gives you this little menu that helps you remember what those I-bound codes are, which is nice. And then the starting head, I'm going to change that to 3,000 feet, because one of the ways that you enter a specified head boundary condition is you change the I-bound value for the cells to a negative number, which we've done, and then you edit the corresponding values in the starting head array to match the specified head you want. So it's a combination of the starting head inputs and the I-bound inputs. So we're going to put that at 3,000 and click OK. And you'll notice when you do that, this little orange symbol shows up indicating that these cells are marked as specified head cells. And if we go into the I-bound array, I'm going to double click on that. You'll see we have ones everywhere except on the leftmost column, and it says -1, showing that those are specified head cells. And if I go to the starting heads array, you'll see we have 3,200 everywhere except for the leftmost column. It says 3,000, and that matches our specified head boundary condition. All right, so at this point, I'm going to go up here to the MODFLOW menu. I'm going to select Check Simulation and Run Check. And what this does, it looks through our inputs to see if we have any errors, obvious errors or warnings. That could be something like you have a starting head value that's below the bottom of the grid, or you have a hydraulic conductivity that's 0 or negative or something like that. So it's always a good idea to run that before you save and run your model. And it looks like we're in the clear, so I'm going to do Save. And if you go to the MODFLOW menu, there's a Run MODFLOW command. You can also access it right over here. There's a little shortcut to it. And we're going to select Run MODFLOW. And when you do that, normally, if you run MODFLOW and you're not using GMS, you'd execute it from a command line, and it would output some text output to the command line. And that output is echoed here in the bottom of this Run MODFLOW dialog. And it took 8 iterations before it converged on a solution. And the convergence error is plotted versus iteration up here at the top. And it says MODFLOW 2000 terminated successfully. You always want to look at that and make sure it terminated successfully, because sometimes it doesn't converge. You know, it blows up, gets off the rails for some reason. And in those cases, you want to maybe investigate what happened. But it looks like we have a good solution, so I'm going to click Close. And when it happens, it reads in the solution. The solution is shown over here on the left in this little window. When I say the solution, these are the output units. So there's the head file, which has the computed heads at each cell in the grid. A CCF is cell-to-cell flow file. That's used to calculate your flow budget. And then there are 2 text files, a GLO file, which kind of echoes the input, and an output file, OUT file, which has the heads in it. And then there's a cell summary CSV, which I won't get into. But generally, it selects the head by default. And so we're looking at contours of head on our grid cells. And you can, by default, it uses this block fill technique to show the kind of the contours of color. And we have a legend over here. So the top is 3180 and the bottom is 3000. So we have this fixed head boundary condition on the left. And over on the right, it goes up to about 3175. Now, by the way, you'll notice right down here, this F field, as I move my cursor over the grid, you'll watch down here and it will show you the elevation of the current data set, which is the head set. So it's showing you the head in feet at every cell I'm passing over, which is kind of nice. You could also go into side view here, and if I zoom in a little bit, you can see the water table elevation along the side. You can also go into the display menu and select display options, and there's this Z magnification factor. I'm going to change it from 1 to 5 and click OK. And what that does, it just amplifies that vertical scale, and let me frame that here. So now you can see, so this is the lake on the left, we have a mountain range on the right, and this is the computed water table surface as you go from right to left, and that looks reasonable. I'm going to go back into plan view and show you some other things. So this little, if you go into the display menu, there's contour options. You can also get to it from right here. And by default is this block fill thing. I'm going to switch that temporarily to this color fill and linear. And I'm going to increase my number of contours up to 20 from the default of 10. And then let's see, I'm also going to turn off my cell edges by undoing that toggle right there. And now we have you can see these contours where the water table is higher on the right and lower on the left. Now this is just kind of a one-dimensional flow field. It just goes from right to left, so it's not terribly interesting, but we'll see more variation as we go along here. Alright, so we'll save our changes there, go back to our instructions, and it says now let's add a well. So we're gonna assume we have a well which is 10 acre-feet per year, which is what has been permitted. So again, we've got to do some calculations here. So if we say 10, let's see, now we'll put this Q for the pumping rate as 10 AFA, acre-feet per year. And that is, and we need to convert that into compatible units. So our length units are feet and our time units are days, so we need cubic feet per day. This is a volumetric input. So say that is equal to, by the way, 1 acre foot is 43,560 cubic feet. So we'll say equals that times 43560. And then that's per year, so we need to divide that by 365, and we get 1,193.4 cubic feet per day. So 1193.4. So now I'm going to, we need to create we're going to put a well somewhere here in the middle. So I'm going to turn my cell edges back on and maybe turn my contours off for a second. And I'm going to use the select cell tool. I'm just going to randomly pick a spot up here somewhere, and I'm going to select a cell, and then I'm going to right click on that and select properties. By the way, actually you can if you want to get properties, you can double click on a cell. But I made a mistake here. It's not properties I want. I'm going to right click on that, and I want to select sources and sinks. So if you select a cell or multiple cells, right click and select sources and sinks, this allows you to create drains or general head, or edit the recharge, edit river, specify head, or also add wells. Now there are 3 different well packages in MODFLOW. We're going to use the simplest one, the WEL package. So we're going to select that on the left and say add BC. BC is like another term for a source sink, like a boundary condition. So I can enter a name. I can put my well. The name doesn't really matter. It's just a label that GMS uses if you want to apply that. And then let's see, what was my pumping rate? 1193.4. So I need to enter that. Now it's really important that you make that minus or negative, because in GMS or in MODFLOW, a negative pumping rate means you're pumping water out, which is what we want. Otherwise, you'd be pumping water in. And we're going to click OK. And it shows a little yellow symbol there. So let's click Save. And let's rerun our model. I'm going to click on this Run MODFLOW button here. Click Close, and it automatically turns our contours back on when you read in a solution. Turn off those cell edges for a second. And what you should see there is there's a little tiny bend in the contours. It didn't make a very big difference. So that 10 acre feet per year, that's actually a pretty decent pumping rate for an agricultural well, but not enough for this particular combination of aquifer properties to generate a very significant cone of depression. So just for fun, let's right click and edit that. Let's go back in and change that. Now, by the way, another way to get to your wells is you can go to the MODFLOW menu, select optional packages, and go down to the well package, and you can edit that here. So let's just increase it by a factor of 10. Let's add a 0 on there. So instead of 10 acre feet per year, it'll do 100 acre feet. Now that's a lot of water, but yeah, we're just playing with it. Let's see how it works. And by the way, I never did turn on the well package. If you go back here to the MODFLOW global options and click on packages, you'll notice that it's on. The reason for that is when you manually create a well somewhere in your grid and you don't have the well package on, GMS will automatically turn it on for you. So that package selection, a lot of times that's just taken care of for you automatically. All right, so let's save that and run that again. And there we go. Now we're starting to see a cone of depression there from our pumping rate. So let's do something else. I'm going to hold down the Shift key, and I'm going to select a couple of other. Whoops! I'm going to select. I'm going to do a Control click. No, it's not going to let me do it that way. All right, I'm going to right click on one of these, and let's do another well here, and we'll do minus 11930. We'll make it the same rate there, and just to make things a little more interesting, let's save and run that and see if we get another cone of depression over there. There we go. Now we got two little cones of depression. Let's see. We could play with the hydraulic conductivity a little bit. What would happen if we decrease the hydraulic conductivity by a factor of 2? So let's go in here, and I'm going to double click. I'm going to change that from 2 to 1, and we'll see what that does to our cones of depression. So we'll save that and rerun the model, and you should notice that the cones of depression changed a little bit, but what happens over here, you'll see all these little blue symbols show up. What does that mean? That means these are called flooded cells. And by the way, if you're ever curious what these symbols are, you can go into the display options dialog, and there should be a where is it? MODFLOW display symbol legend right there. So you click on the MODFLOW tab, display symbol legend, and down here it says, okay, you've got 3 symbols here. You've got the constant head cell, the wells, and also flooded cells. So these, what that means is for these cells, the computed head is above the top elevation. So if we go into side view, you should see this. There we go. Let's see, it's not showing the grid. Let's turn the grid cells back on, cell edges. There we go. So notice, starting about right here and going to the right, the simulated water table is above the top of the grid. Now, assuming the top of the grid is your ground surface, that's a real problem. And why did that happen? What did we do? We reduced the hydraulic conductivity. If the hydraulic conductivity is smaller, that means it's less permeable. And so remember, we have recharge coming in on the top, and it's flowing from right to left. So if it's less permeable, it causes that water table to back up. And to illustrate that, let's go in and now let's, instead of reducing it, we started at 2. Let's change it to 4. So instead of reducing it by half, we're going to double it. Now watch what happens. We're going to save and run this. And what should happen here is we should get a much flatter water table. And look at that. Now it's much more flat. And if we go back into plan view, we still have contours, but if you look at the values here, it's 3090. It used to be 3175 on the right. So it's much more flat as you go from right to left. And now if we went in and changed the recharge rate, we'd see the same kind of thing. So I'm going to change the hydraulic conductivity back to our initial value. But I'm going to go into the recharge rate. Let's see, this is 0.00685. Let's change that to 0.003. So a little less than half of what it was before. So we have less water coming in. Whoops, I need another zero there. 3 zeros and a 3, right? There we go. So we get about half as much water coming in. Let's see what that does to our solution. We should end up with, yeah, there you go. Now on the right, the head is 3068. So we've gone from 3175 down to 3068. So reducing the recharge is kind of like increasing the hydraulic conductivity. It makes our water table more flat. You get less mounding as you go from right to left. So anyway, so you could continue to play with some of the different options here. But hey, we were able to create a simple MODFLOW grid, created a simulation, added a well or two, looked at what happens when we change the hydraulic conductivity and recharge. This has been a nice little introduction to MODFLOW. And so we'll stop here and we'll come back later with another set of exercises to keep on improving your skill with and exposure to MODFLOW models.